In this lecture, we're going to talk about different features of airfoils. One important thing is the angle of attack. This plays a big impact on the coefficient of lift for an airfoil. And if you look at this figure, there's three different airfoils here, and the coefficient of lift, depending on that angle of attack, the angle that the airfoil makes with the ground. What you can see right off the bat is higher angles result in a higher coefficient of lift. You'll notice that with an asymmetric airfoil, you do get lift even with no angle of attack. And you have to actually point downwards before you get a zero lift, before there's no lift at all. But if you tilt it upwards more, you get increasing lift until at some point you actually reach this phenomenon called stall. And you'll notice those lines stop at around around 15 degrees. Something unusual happens at this point. If you tilt the wing too high up, as the air flows around it, it's not able to make that sharp turn and stick with the airfoil like it's supposed to. If it's too sharp a turn, it actually peels off and we're left with this vortex behind the wing. That causes all kinds of problems with the wing. So having a wing stall, that means we get boundary layer separation. We have the airflow peeling off the wing with a vortex forming behind it. We get a wide turbulent wake behind the wing. And you get a rapid increase in drag and a rapid decrease in lift all at the same time. And those are pretty bad things that that can happen while you're flying. So you get a huge increase in drag and a decrease in lift. Also keep in mind that stall has other definitions. So right now we're talking about the wing stalling, and that has to do with just how fluid is flowing around the wing. You could also have the engine stall, but that's a completely different phenomenon, right? That has to do with the engine stopping. Here's a photo of an airfoil underwater, and this has stalled, and the pressure on top of the wing has actually gotten so low that we've had you can see cavitation there, that the water is boiling, forming water vapor as the vapor pressure has been exceeded. Okay, area is another important property. It's in our lift equation. For airfoils, we typically use the plan form area. If you remember, that's the bottom area. So if you look at a wing, this is the shadow that the wing projects downward. So that's typically what's used in our lift equation. And just a little bit of terminology. The distance from the width of the wing is called the chord length. And again, that's not the bottom perimeter. It's just the distance through the center of that shape. And if the length of the wing is called B, you have to actually do some integration to come up with the area, because the chord length changes along the length of the wing. But if we use the average chord length, we can think about the area being B times C. Another useful parameter for airfoils is the aspect ratio. The aspect ratio is defined as the length of the wing squared divided by the area of the wing. And if we use the simplification from the previous figure, or from the previous slide, that's the length of the wing divided by the width of the wing. And it turns out that the most efficient wings are high aspect ratio wings. High aspect ratio wings result in high coefficient of lift and low coefficient of drag. So these are the most efficient, and they're typified by long, narrow wings. Those provide the most lift and the least drag. Short, fat wings are very inefficient flyers. And that's shown in these figures here. You can see three different airfoils with three different aspect ratios. And if we're talking about coefficient of lift, the higher aspect ratio produces the most lift. If we look at the drag figure, the highest aspect ratio produces the least amount of drag. So here are two flyers with very high aspect ratio wings. Top is an albatross, which is probably the most efficient flyer in the animal kingdom. These guys have the longest migratory routes of any animal. They actually migrate all the way around the world. I think they cover about 20,000 miles a year. And then below it is a glider, which is such an efficient aircraft that it doesn't even need forward propulsion. Gliders can only work if there are updrafts that it can take advantage of, but a good pilot has no problem making use of that. So you can see right off the bat, these are long, skinny wings, high aspect ratio. They're very efficient, and these are great for conserving fuel over long distances. The glider is so efficient, it doesn't need any fuel. So if the best wings are these high aspect ratio wings, why in the world would we make other wings that are short and fat? Why would this bird of prey, this merlin, why would he want short fat wings if they're so inefficient? Well, there is a downside to the high aspect ratio in that they make slow turns. It's hard to get those big long wings around. So low aspect ratio flyers, they're inefficient airfoils. It takes a lot of energy to keep them in the air, but they're highly maneuverable. And for a bird of prey and for a fighter jet, that is much more important than being efficient. In fact, the F-16 below, I'm not even sure if those wings provide any lift at all. It's got so much propulsion that the wings aren't really needed for lift. Okay, another important property of airfoils is lift-to-drag ratio. Now, if you purchased an aircraft or if you are shopping for one, this is something you would look for. The coefficient of lift divided by the coefficient of drag gives you this lift-to-drag ratio, and it's an important property of any aircraft. And that tells you the minimum glide slope for unpowered flight. The glide slope is the angle of descent. And so if we take an aircraft, let's say there's no updrafts and it's not powered, so this is just going to glide down to the ground, it's going to follow a certain trajectory. And that trajectory has to do with the design of the aircraft, more specifically the lift-to-drag ratio. So the glide slope is actually that angle that it forms with the horizon as it descends. With the lift-to-drag ratio, you can calculate exactly what that angle is going to be using this equation. And what it tells you is that for every foot of descent, you'll get a certain amount of forward movement. So let me do an example where you can see this, how to use this. It's quite simple, actually. Let's say you're flying a plane at 20,000 feet. It's got a lift-to-drag ratio of 20, and the engine stalls. How far can you glide to make it to a landing strip? Well, since the lift-to-drag ratio is 20, we know it will glide forward 20 feet for every 1 foot that it drops. So this is pretty straightforward. We start at 20,000 feet. We're going to descend all of those 20,000 feet, and we'll move 20 feet forward for each of those foot dropped. That works out to 400,000 feet or 75.8 miles. You could also solve this with trigonometry by using by solving for theta using the previous equation, and you'd come up with the same answer.